Alright, so we got a quick video to watch that'll help you with both worksheets that you picked up. If you didn't pick up a worksheet, it's sitting on the outside of the classroom, most likely. First thing is substances that's in your reaction packet is supposed to be due today, Tuesday, but we can bump that to tomorrow, Wednesday, just in case you have any final questions that I can answer in large groups. So I'll go over that just a little bit, but it would be wise to have as much of that done as you possibly can. You're receiving a worksheet that is about nuclear chemistry. You need to finish that up for this evening and hand that in tomorrow. All right. The other worksheet about coordination compounds, that is not technically due. That is just a note reference sheet for you. All right. So let's get going. First thing we're going to do is we're going to look at our nuclear worksheet. Okay. So nuclear chemistry is a really interesting and very in-depth field, and we are going to hit extreme shallow basics of that today. AP Chemistry does not require a lot of that from you, but I do need to give you what is needed. And what it really is just about writing equations, okay? So do you understand how it kind of works with equations? So there's some different isotopes that occur in nuclear chemistry, and usually you can figure them out regardless of the names, but there are a few that really are important, so they are on the top. So the first one is called an alpha particle. And an alpha particle is actually a helium isotope, and you see a unique kind of writing with that. There's a superscript and a subscript with 4 and a 2, and then the actual symbol of the element. I want to quickly review what those mean. We learned that a long time ago in first year chem, and may have just touched on it just slightly this fall. So the top number, if you look at the periodic table, you probably realize, hey, that the 4 kind of looks like the mass, and the 2 kind of looks like the atomic number, and that's just more or less what it is. The superscript value in an isotope is always the mass number. Translation, that is the protons and the neutrons. And the subscript value is always the atomic number, which is just the protons. Sometimes you'll actually see an isotope without that bottom number because it's kind of redundant. If I say helium, it always is going to be 2, but the upper number may have different values. An isotope, by definition, is an atom with the same number of protons but different number of neutrons. So an isotope would have different neutrons, but the protons would have to stay the same, so the mass number would be the one that would change. A beta isotope is basically an electron. That's all it is. So you don't have any neutrons, and then it's actually a -1, so you're actually removing a proton, which gains negativity in a way. A way to think about that is you go from a nuclear change of 0 starting point to a -1, so you'll be losing charge or be gaining negativity. Okay. A gamma particle looks like this. I would suggest writing it more like that Y. It's an upside down lambda from earlier in chapter 7 with wavelengths and frequency. They have 0 mass whatsoever. So it's more about just radiation, massless radiation. It's just energy. Okay. Positron is the opposite of a beta. You'll have a positive change in your nucleus. So you go from a nuclear charge, I should say. You go from a 0 to a +1. And then finally a neutron. Neutron is just simply what it says. You're not gaining any protons, but you're gaining neutrons. Please feel free at any time during this video, if I'm going too fast, please just pause it and fill it in, and then continue when you need to. I'm only going to do 2 problems for you here just to give you an idea. So let's take a look at number 1. Here's the trick. Nuclear reactions usually are reactions that break down atoms or isotopes. We'll call them just isotopes for now. So you'll see this on the left. I have uranium. And just as a quick review on this, how would I name that uranium? You would say uranium-238. You say the symbol and the mass number. So this is uranium-238. All right, well, you see 238 there and 92. Well, it breaks down, and what I have here is 234 and 90. And TH represents 90 because that's the atomic number of TH. All right, but what would be in the box? With anything, you never lose or gain. You maintain the same before and after reaction. So 238, and there's only 234, it would make sense there would be a 4 for my superscript. 92 and 90, there should be a 2 there. Well, then that makes sense that there'd be a 4 and a 2. Well, why do I know it's helium? Because there's a 2 here, and 2 corresponds to helium. Well, this itself is an alpha particle. So this is an example of alpha decay. And what that means is when you are creating a product, if one of these up here exist in the products, then you can say that is blank decay. So you can fill out many of these as you go, and that's your homework. But we're going to go down all the way to number 8. And what this one says on the side gives you a little hint. Neutron bombardment. Let's look at that. When you're bombarding something, you're hitting it with it. So a beam would be hitting this boron isotope with a neutron. So here's my isotope, and I'm bombarding it with neutrons. And it says with alpha emission. Here's my alpha emission. All right, so you're like, well, what else to fill out? What is the resulting isotope of this? Well, how do I figure that out? How I figure that out is based on simple math. 1 plus 10 is 11. So the superscripts over here need to equal 11. Blank plus 4 equals 11. Well, that should be 7. 0 plus 5, so that's 5. Blank plus 2, oh, that's 3. So 7 and 3. Well, which number helps illustrate the element? It's the bottom one. It's a 3. So this should make sense that it's 7 and a 3, and it's lithium. The 3 indicates the lithium. So that's how we figure this out. You guys should do pretty well filling out the rest of this. This is the extent that we need for nuclear chem. All right, let's quickly move on to the other one. Again, if I'm going too fast, please just pause. These are coordination compounds. It's more complicated than this, but basically what you have is these are compounds that are more complex. They do not follow the octet and what we understand as bonding the way that we've been learning it. So coordination compounds are usually formed from a transition metal surrounded by ligands, and a ligand is usually a neutral or an anion, and it actually acts, here you go, polar molecules are negative ions, and they act as Lewis bases because they will share electrons. Okay, they give away their electrons. Don't worry too much about the colors, but you do need to know this, and most of them really do make sense. This is not all that tricky. Your job is just to understand if there's a common name. Your job is to do the names. On Wednesday, we will go through the equations, the writing of reactions in your reaction packet, okay? So aqua, hopefully it makes sense to you that that is H2O. Amine, you will need to know this. It's NH3, it's ammonia. And then, okay, these say all anions. So fluoro, chloro, bromo, iodo, hydroxo, and cyano. Hopefully this makes sense. F minus, Cl minus, Br minus, I minus, OH minus, and Cn minus. Pause it if you need to. Please write those in. Here's the real trick. Whatever the charge is of my center atom, which will be a metal, usually the number of ligands that attach to it are twice as many. So here are two great examples. You have CuNH3,4. Well, it says it's 2+. NH3 is a neutral molecule, so it doesn't add to the charge. Well, if this metal is 2+, I have 4 that are attached. Hey, silver is a +1, so I attach 2 amines. All right, so there's a bunch of rules with naming. I just want to show you how to do it. We'll practice it more actually later. I'd like you to put this on the side burner until tomorrow, but just so you see this now. Okay, so this is a full coordination compound. A complex ion is the first part here. but it's bonded to the Cl. Okay, so long story short, let me show you how this is named. All right, we're going to go backwards. So here's the chlorine. It's monochloro. Again, you don't really have to worry about as complicated in names as this necessarily. You have 5 amines, so pentaamine, and then cobalt. Why is it cobalt? Well, I'm sorry. It's actually cobalt 2. It's cobalt 2 chloride. The reason why is that it had to crisscross still, and here's a 2 from this ion here, this complex ion, and it crossed down to the 2 for the chlorine. So this is the complex ion. That's right here. And then there's the leftover, the chlorine. Okay. Let's take a look on the bottom. How do I do an ion? This you'll kind of be more responsible for. How would I actually do this in formulas? So formulas are probably more important because usually you're given the names and you have to give a formula. So to wrap this up, hexa aqua cobalt 3 ion. Okay. So what you do is, like up here, it's usually the metal first, then the ligand, but you name the ligand first and then the metals. So it will start with cobalt, and then you should have 6 waters. So here's a cobalt, there's 6 waters. Why is it 3 plus? Because the water is neutral. So cobalt would have the 3 plus. Please don't worry about the rest of this at all. Please put this on the back burner. We will go over the reaction writing on some of the even numbers for you in your reaction packet on Wednesday. All right, so work on your nuclear worksheet, please, and have that ready for tomorrow. Your substances can be due on Wednesday instead of today. All right, have a great day, you guys. I will see you tomorrow.